Yeah. All right. So here, back on Friday, we were just starting a question that dealt with well, this rotational dynamics I said, right? There was a lot of little parts involved with it. So let's get a good look here. I've got two posters that you guys need to be real familiar with it. That we're getting to kind of complex concepts. This is from December, Unit 7, rotational dynamics. So review right here. Suppose you have this turntable and you wind a string around it, right? Because you're pretty much like for sure you're going to get asked this question on the AP exam, right? They're going to ask some version of this question. You wind a string around a turntable and you pull it with some force, right? Doesn't that create a torque, right? R cross F. Okay, so that's torque is R cross F, right? Now there's another perspective on torque, which is I times alpha. So this R cross F caused by pulling the string results in I times alpha, this turntable spinning, not just spinning, but speeding up spinning. That's what alpha is, right? Angular acceleration. Is what's the unit for angular acceleration? Radians per second squared, right? Could be speeding up spinning, right? Or maybe slowing down spinning if it's like a frictional torque, something like that, right? All right, now there's this other concept we call capital L, stands for angular momentum, right? I times omega, isn't that analogous to linear momentum, right? So let's here, write this on a piece of paper. You guys got notes out, right? You guys got notes, right? Let me write some stuff here. So think about linear motion, and then here you guys are looking at rotational motion, right? Angular motion. Right? See what parts are equivalent to what. So we got linear momentum could be mass times velocity. There's mass times velocity, right? I don't know. I'd say a change in momentum, like back to linear stuff, right? That's also called impulse. Was mass times change of velocity, but that came from applying a force for some time interval. Right? You guys remember that too? Right? Now, what's the rotational equivalence to all that? Oh, well, I got capital L for angular momentum. That's I times omega, right? So now we're talking about in a rotational sense, how much inertia. It's kind of like mass, but now it's rotating. So it's some of them are squares, what that was, right? And instead of saying how fast meters per second, now we're saying how fast rotating radians per second. Right? And if you want a change in angular momentum called angular impulse, right, setting up the question that we were partway through back on Friday, right? You could call it I times change in omega, right? Kind of analogous to the linear version on the left side. Right? Or the flip side, the perspective of this is delta L, change in angular momentum, angular impulse is equal to, right guys, what am I able to write in this, what fills in this blank space right here? If you're completing the pattern, what do I write? What times what? Yeah, I times delta omega. Or what's the other perspective? Here's a hint, right? You guys remember linear impulse was mass times change velocity that came from applying a force for some time interval. What's the rotational equivalent of that for this turntable situation? Torque times time. Torque times time. Right? Right? Okay. You guys know that? Right? This is analogous, analogous, analogous. Right? You guys know that? Okay. Okay. And then looking at this torque right here. Okay. Of course, we could pull that out and say, well, that's torque equals R cross F. Right? Back to this string turntable. Zoom. Right? And also remember, torque equals I times alpha. All right. So there's a lot of stuff going on there. Right? You guys see that? A lot of stuff. Right? I've even seen AP ask questions before. You guys remember these type of questions too, like what's the linear analogous situation to this rotational situation, something like that. Okay, you guys know that? Okay. And before I flip my screen, also here show you guys this pair of graphs side by side. Here, pause here. Boom. All right, back here. All right, so this could be for a scenario where maybe let's look at this picture to attach a story to this. Right, maybe you have like some turntable with a string and pulling with a constant force. Because if it's a constant radius and a constant force, isn't that like a constant torque? Right? Which is what this graph is showing. I mean, you could get a little bit more complicated version of that. This is pretty straightforward, right? And then as you pull with a constant torque, that's going to speed up rotating, right? Maybe an angular acceleration it'll have, right? Which means that it's gaining angular momentum. This L is increasing. This capital L. That's increasing at a constant rate. And here's the connection between these two graphs. Both of these graphs apply to the exact same story, right? Right. There's two different perspectives. You can see the connection. Here's angular momentum increasing area under this curve, right? And it's according to this curve. And here's the torque on this curve. Is the slope of well, that curve, right? Which represents this coordinate on this curve, right? So you guys see the connection, the graphical connection between torque and angular momentum, right? You guys know these two graphs, Again, the story this goes to is pretty basic story of you're just playing a constant torque and this thing spinning. Okay, right, you guys got that? All right, now we're ready to flip over to AP Classroom.